Hello and welcome to another digital design class. In the previous classes, we learned about binary systems, the conversion of decimal and hexadecimal to binary. And why do we actually need to convert everything to binary? The reason is because computers work on different levels of voltages and they work on a binary system. We learned about logic gates, and, or, not, XOR, XNOR. And we learned about Boolean algebra. And also about the algebraic manipulation. And the reason that we are learning this is that we want to be able to design a Boolean function that has minimal literals and minimal terms. So we would have the minimum number of gates. Again, we want to simplify our system to have the minimum number of gates, because minimizing the number of gates creates a faster, more efficient, and reliable and cheaper computer. We learned about Boolean algebra, different postulates and theorems, and how we can utilize them to minimize the number of terms and literals that we have, or to actually minimize and simplify our Boolean function. We solved some practice problems on how to simplify Boolean functions. So for example, this example that we solved, this one we have 1, 2, for example, 3 gates, and we replace it with 2 gates, for example. So we reduce the number of gates. This is an example. For this example, we have 1, 2, let's go back to the original question. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 gates. And we are able to simplify that to a simple input of A. Okay, so it's going to be a huge difference sometimes. Sometimes you reduce it by 10, 15%. Sometimes you reduce it significantly. And we also learned that sometimes you don't have a single answer. You may have 2 answers, but both of them are maybe correct as well. Today, we're going to learn another approach on how we can simplify that. So manually doing that using different theorems and different postulates, and using this table that we already went through. Just going to go back so you can remember the table that we have, the postulates and theorems of Boolean algebra theory. It's difficult to memorize this. It's difficult to manually simplify functions, sometimes when you have a very large function. Another approach is to use what we call a K-map or Karnaugh map. And to learn that, we first need to learn about minterms and maxterms and sum of, or what we call sum of products or product of sums. So today we're going to start with the complement function. Then we will go through minterms, maxterms, and if we have time, we will go through sum of products, which is sum of minterms, or SOP we call it, and POS, which is product of sums. We already learned about the complement of a function, which was done using a De Morgan's, what we call a De Morgan's theory, or theorem number 5. And what does De Morgan theory show? It shows that if we have, for example, x plus y prime, we can write it as x prime y prime. And we can also expand that as well. So for example, if we have a plus b plus c, or a or b or c, all of that in a parentheses prime, we can replace b plus c with x. And using the De Morgan's theory, a plus x prime is equal to a prime x prime. Again, we will substitute x by b plus c. So we have a prime and with b plus c prime. Again, b plus c prime is equal to b prime c prime. Let me write it somewhere else. So b plus c prime, both of them are in the parentheses, and the prime is on both of them. Sometimes we write it like this. Sometimes we can write it like having a bar on the top as well. Both of them are the same. This would be equal to b bar c bar, or b prime c prime. So therefore, we have a prime times b prime c prime. Now with the associative law, we can say that that is equal to, and get rid of the parentheses, we would have a prime, b prime, c prime. So in general, a function is obtained by interchanging the and with the or and the ors with the ands. And also by complementing each of the literals. So for example, if we have a plus b plus c plus d plus f, all of that in parentheses prime, it's going to be a prime b times b prime times c prime, or a prime and with b prime and with c prime till f. And the opposite is also true. So we interchange the ands with the ors when we have the complement, and we would complement each of the literals. So a and with b and with c with d and f prime in the parentheses is going to be a prime plus b prime plus c prime plus d prime, and so on. Now, let's do some examples together. First example, f1 prime is equal to, f1 is equal to x prime y z prime plus x prime y prime z. We want to find f1 prime. So all of that, we want to find its complement. So first step, when we put a prime, this or sign becomes and sign, and the literals become, we have to find the complement of each literal. So if I want to find the prime of this literal, and becomes or, and each literal becomes its complement. I'm sorry, each literal in the term becomes a complement. So it's going to be x plus y prime plus z, and with x plus y plus z prime. So again, all the ands become or, and all the variables or literals, we have to replace them with their complement. So x becomes x prime becomes x, y becomes y prime, and y prime becomes y, etc. Now, I want you to think on this for a few minutes and then solve f2 prime for me. So f2 is equal to x, y prime, z prime plus y, z. We want to find f2 prime. I will give you a few minutes to think on this, then I would start solving it. Again, the first student to solve this gets extra points on their next homework. Very close, but not the final answer.
You want to factor that out.
You have to, yeah.
When you do that, is that x prime outside? Like,
It's not correct.
not like that.
No.
Not with,
You have to do it completely separate. You shouldn't multiply this with these first. You have to first do it separately and then, yeah. But it's very close, you know. You have one extra step. It's very close. Not the exact answer, but very, very close, yes. Does anyone have the answer? Do you want me to solve it? Yeah, what do you have?
Up with x prime plus yz prime plus cy prime.
Perfect. Yes, perfect. That's correct. Yeah. So the first thing, we have an and over here, and we have to, again, convert all the ands to the or. So we're going to have x prime plus, and we're going to keep the next one, y prime z prime plus y z, and all of that, we have to find its complement, prime. Again, we have another or over here that we have to convert to and. So we're going to have x prime plus y prime z prime prime and with y z prime. Again, we have the ands inside the parentheses. So this would be equal to, again, x prime plus y plus z multiplied by y prime plus z prime. And if we simplify them, these two, this is a correct answer, but if we want to simplify it one step further, we can have x prime plus y times y prime gives us 0. Y prime, we know it's 0. So we're going to have y z prime plus, and again, z times z prime also gives us 0. Time plus y prime z. This is going to be our final answer. X prime plus y z prime plus y prime z. There is also a simpler way to do that. It's to use the dual of the function, and then we can complement each literal. So a simpler procedure is, for example, we find the dual, meaning all the ands are replaced with ors and all the ors are replaced with ands. And then, so the complement of f1, which is x prime y z prime plus x prime y prime z, is equal to x prime plus y plus z prime, and with x prime plus y prime plus z. Now we would complement each literal, therefore we're going to have x plus y prime plus z, and with x plus y plus z prime, which gives us f1 prime. Now I want you to do that for f2. F2 is equal to x times y prime z prime plus yz. What is f2 prime equal to? Yes. F2, very close. You have to replace all the ands with ors and ors with ands.
This was an and, that's an or,
Mhm.
so that becomes an or, and this becomes and, right?
Yes, but what about the ands in between these?
Oh, between them.
Mhm. Okay, so from duality, we will replace all the ands. By the way, we have an and here, one here, so we have three ands with ors and ors with and. So this or with and. So it's going to be x plus y prime plus z prime and with y plus z. Now we will complement each literal. So we're going to have x prime plus y prime, I'm sorry, y plus z and with y prime plus z. Is there any question? Can I go to the next slide? Okay. So now canonical and standard forms, we have the minterms and max terms. A minterm is also called a standard product. It's an AND term, and it consists of all the literals in their normal form or in their complement form. So for example, two binary variables, x, y, the minterms are xy or x prime y prime or x prime y or x y prime. So we have two variables or literals, x and y. Therefore, we're going to have 2 in the power of n or 2 in the power of 2 combination, which is 4 combination. It could be xy, x y prime, x prime y, and x prime y prime. So again, it's an AND term. So they have to be multiplied. And the variable could be in its normal or in its complement form. So it could be x or x prime or y prime. This is also called a standard product. And when we have n variables, we have 2 in the power of n combinations or 2 in the power of n minterms. So when we have 2 variables, we are going to have 4 combinations of them. And the max term is a standard sum, or the standard sum is an OR term. Again, if we have 2 variables like x and y, we would have 2 in the power of 2 or 4 different combination of max terms. And it's going to be x plus y, x plus y prime, x prime plus y, and x prime plus y prime. We're going to have 4 different combinations, or 2 power of 2 or 4 max terms. Now, what if we have 3 variables, x, y, and z? How many max terms would we have? How many combinations would we have if I have 3 x, y, and z?
8.
Yes, thank you. 2 in the power of 3, we would have 8. And for 8, it's shown over here. So you can see that if I have x, y, and z, I would have 8 different max terms and 8 different minterms. And we show it with the minterms, we show it with the lowercase m from m0 to m7, which gives us 8. And for the max terms, we show it with the capital or uppercase. Again, we have 8 different combinations. And the interesting part here is, let's say if m0 is equal to x prime, y prime, z prime, and I want to find m0 prime. So m0 prime is going to be the x prime, y prime, z prime, prime. Using the duality, it's going to be x prime plus y prime plus z prime. And then complementing it, it's going to be x plus y plus z. So we can see that m0 and m0 are the complement of each other. So m0 prime is equal to m0. Or m0 prime in the same way, from duality, it's going to be equal to m0. So the minterms and max terms are the complement of each other. Now, m0 is showed with x prime, y prime, z prime. m1 is showed with x prime, y prime, z. m2 is equal to x prime, y prime, x prime, y, z prime. m3 is x prime, y, z. m4 is x, y prime, z prime. m5 is x, y prime, z. m6 is x, y, z prime. And m7 is x, y, z. So what do we see here? We see that when we have the prime or the complement, then the literal itself is going to be 0. So 0, 0, 0 gives us x prime, y prime 0, y prime, z prime. And 1, 1, 1 gives us x, y, and z. So you can see that if you have a complement, it's a 0 in the table. And if we have the literal itself, it's a 1. So let's see, if x, y, and z are 0, 0, 0, what would x prime, y prime, z be? So x, y, z is 0, 0, 0. What is x prime, y prime, z prime equal to? Let's replace it. So if x is 0, then x prime would be equal to what? If y is 0, y prime would be equal to what? And if z is 0, z prime would be equal to what? 1. And 1 multiplied by 1, and with on, it's going to give us 1. Now let's do it for another minterm. Let's say m5. X, y prime, z. What is x? It's 1. What is y prime? Y, 0. Therefore, y prime would be what? 1. And what is z? 1. So x, y prime, z gives us what? 1. So if I multiply, do all of these, all of them would give us what? And you could check it for any of these. Now let's do it for max term. If x, y, and z are 0, 0, 0, what would m0 be? 0 plus 0 plus 0 gives us what? 0. If x, y are 0 and z is 1, we have 0 plus 0 plus 1 is z, so z prime would be 0. So this would be equal to 0. So in the same way, all of these would be equal to 0. Like x prime, y prime, z prime, when x is 1, x prime would be 0. When y is 1, y prime would be 0. And when z is 1, z prime would be 0. So 0 plus 0 plus 0 again gives us 0. And it's obvious because these two are a complement of each other. So if this is 1, the minterm is 1, max term should be 0 because they're opposite of each other. Does it make sense? Yes? Okay. You may think, why do we need this? And we learn, I would show you in the K-maps that these are very helpful when you want to simplify Boolean functions. It's going to help you a lot. And you can literally write any Boolean functions using just minterms and maxterms. And I'll show you with some examples how we do that. So a Boolean function can be expressed by a truth table or sum of minterms or the product of sums or product of maxterms. So for example, here we have two different functions, f1 and f2. And f1 is 1 when we have m1. It's 1 when we have 2, 3, m4. And it's 1 when we have m7. So f1 would be equal to m1 plus m4 plus m7, which is written over here. You can just look at this. And the same way for f2. f2 is equal to when we have m3, m5, m6, and m7. And it's 0 in the rest of the table. So we can write it as a sum of these minterms. We can have these functions. So the complement of a Boolean function, the minterms that produce a 0. So for example, f1 prime is m0, m2, m3, m4, m5, and m6, which is equal to x prime, y prime, z prime plus x prime, y, z prime. Again, this is m0. If you go back to this table, this is m2 because it's 0, 1, 0. This is 0, 0, 0. This is 0, 1, 1, which gives us m3. And this one is 1, 0, 1, which is m5. And this one is 1, 1, 0, which is m6. Now, f1 would be f1 prime prime, which gives us x plus y plus z, and with x plus y prime plus z. Now, what does this mean? If we have a minterm again, its complement would be its max term. So if I have m0 plus m2 plus m5 plus m6, the max term, the complement would be m capital m0 plus capital M2 plus capital M5 plus capital M6, for example. And we have it here as well. So F1 prime would be equal to F1, which is, again, the max term of the same. So same numbers, but this time, instead of having the min terms, we have the max terms. So any Boolean function can be expressed as a sum of min terms, or we call it sometimes SOP, or sum of products, because the midterm is also, as I mentioned here, is a type of product or a standard product. Or we call it a product of sums or product of maxims, or we call it POS. So a sum of minterms of sum meaning the ORing of terms, or a product of maxterms, a product meaning the ANDing of terms. Both Boolean functions are said to be canonical in a canonical form. And I will solve some practice problems so you get used to it. For sum of minterms, there are 2 to the power of n minterms and 2 to the power of 2n combinations of functions with an n Boolean variable. So for example, we want to express f equal to a plus b c prime as a sum of minterms. So to show this as a sum of minterm, we have to have at least 3 different minterms that has a, b, c, that has all the literals. The first part, a, is missing b and c. Okay, so what we can do, this is not a sum of products or sum of minterm. We have to expand it. So the first thing that we have to do, we have to write it like this: a multiplied by b plus b prime. And we know that b plus b prime is equal to 1. Therefore, a times 1 is equal to a, and it won't make any difference. It's like the same thing. So we just multiply that by b plus b prime plus b prime c. This would be equal to ab plus a b prime plus bc prime, not b prime c. Now again, these terms don't have c, so what we do, we would multiply it by c plus c prime. So we're going to have a b times c plus c prime, I'm going to write the rest here, plus a b prime times C plus C prime plus B C prime. Now for B plus BC prime, again, we don't have A plus A prime, A and A prime, so we're gonna write it like this. We're gonna write it like A plus A prime times B C prime. And the final answer would be A, B, C plus A, B, C prime plus A, B prime, C plus A, B prime, C prime plus A, B, C prime plus A prime, B, C prime. Now, what is ABC equal to? M7. ABC prime, which is 1, 1, 0, it's M6. A, B prime, C, which is M5. A, B prime, C prime, which is M4. A, B, C prime, which is 1, 1, 0, again, it's M6. And A prime, B, C prime, which is 0, 1, 0, which gives us M2. So we can write F as equal, it's equal to the summation. One way to write it is like this: 2, 4, 5, 6, and 7. See if I did it right. Okay, so here, just to clarify, this is solved for A plus B prime C. So there is a small typo here. Just eliminate this and replace it with A, B prime C. So I solved it for A plus BC prime. This is for A plus B prime C, which gives us sigma of 1, 4, 5, 6, 7. And I solved it for the question AB plus BC prime. So if you see a little difference, because this is A plus B prime C and mine was for A plus BC prime. Now, if we want to write the truth table, when we have the midterms, we're going to have 1. So the midterms here would be at M1, M4, M5, M6, and M7. So at M1, 4, 5, 6, 7, F is equal to 1, and the rest is 0. Now, let's do another expression, another example. We want to express this as the sum of products. And again, sum of product, or SOP, of F equal to AB plus C prime. AB plus C prime. Let's make it A prime B plus C prime. A prime B plus C prime. And I want you to write the sum of product of this and the truth table for it. Again, write the SOP of sum of products of f, function f, which is a prime b plus c prime. Did anyone have solved it? No. So f would be equal to a prime b, and it's missing c. So I'm going to add c plus c prime. And c prime is initially missing a, so I'm going to add a plus a prime. And therefore, we're going to have a prime b c plus a prime b c prime plus a c prime plus a prime c prime. Again, these two terms are missing b. So again, I'm going to write it like this. I'm going to multiply these two by b plus b prime. So this multiplied by b plus b prime, and also a prime c prime, again, and with b plus b prime. This would be equal to a prime bc plus a prime bc prime plus a b c prime plus a b prime c prime plus a prime b c prime plus a prime b prime c prime. Now, which one of these look the same? This one and this one are the same. So we could just write down one of them. Yep, and that's it. So a prime b c prime, this is 0, 1, 1, gives us m3. A prime b c prime is 0, 1, 0, which is m2. A b c prime is 1, 1, 0, which is m6. A b prime c prime is 1, 0, 0, which is m4. Again, this is the same, m2. I don't need to write it. And a prime b prime c prime is m0. So f would be the sigma, I can write it like this, of 0, 2, 3, 4, 6. 0, 2, 3, 4, 6. And this is 0, 1, 0, so it's 2. This is 1, 1, 0. Again, 1, 0, 0, which is 4. 0, 1, 0, which is 2, and 0, 0, 0, which is 2. Now, for the product of sum or the product of max terms, again, we can write it as POS as well, product of sums. It's going to be the same. We can use the distributive law to expand. Again, for example, x plus yz. Using the distributive law, we can write it as x plus y and with x plus z. And we are missing a z here, so it's going to be z plus z time and with z prime. And we know that z and with z prime gives us 0, so it's not going to make any difference. And this term is missing the y, so we're going to add it with y prime. And then we can expand it again, and it's going to be x plus y plus z. And with x plus y plus z prime, and with x plus y prime plus z. Again, can use the distributive law again. Now, I want you to solve it for example 2.5. We want to express f equal to xy plus x prime z as a product of sums, or POS. And again, I'll give you a few minutes to think on it. And again, whoever solves it gets bonus points on the next homework. And by the way, remind me to give you the bonus points when we get to the exam. I would add it to your first exam.
Is this why this works? But this is the, thing.
Mm. What is the final answer? What is the final answer?
Oh, I'm working on this.
Yeah.
This is the, or, yeah,
Yes, yes. This is a distributive
But-
law.
I wanna go from here to here.
I did the proof for the distributive law.
But when we have this x plus y plus z,
1 x times 1 is going to
that
be 1.
what,
Yeah, you can
that
use that.
y that does that.
Yeah, almost. No.
So how do we get rid of that?
I already did the proof, but I can do it again if you want. Yeah. But technically, if you multiply these two, you're going to have xx, which is x, and then you're going to have xz, and you're going to have yz. Okay.
What about xy?
Again, you have the, I'll go back and give you the theory for this. But technically, what you can do is you can multiply everything by 1, as you mentioned here, or you can use a distributive law. And I will go back through that as well. Yeah. What is the answer for this? Does anyone have the answer? I'll give you a few more minutes. You can also prove it with the truth table as well. You can prove all of these by truth table. Just put A, B, and C, and you would see that
What symbol do you use for the product? Like for the sum, we use.
it's an
a sigma.
and the multiplier. Yes, it's like a pi.
Oh,
Did anyone solve it, or do you want me to?
is it M0 times M2 times M4 times M5?
Perfect. Yes, that is correct. Yes. So F would be equal to xy plus x prime z, which I can write it like this: xy plus x prime z. I can write it like this. It's going to be xy plus x prime times xy plus z. Which is going to be equal to x plus x prime, x plus x prime, which gives us 1, times y plus x prime, times x plus z, and I'm going to do the rest here, times y plus z. Let me finish, then you can write it, because I want to double check it as well. And this would be equal to x prime plus y times x plus z prime times y plus z. And x prime plus y is equal to x prime plus y plus z prime, because we are missing z. And this would be equal to x prime plus y plus z, and with x prime plus y plus z prime. Therefore, f would be equal to x plus y plus z times x plus y prime plus z times x prime plus y plus z times x prime plus y plus z prime. This is M0, this is M2, this is M4, this is M5. So the final answer, I'm going to write it. Let me see if I have. Yeah. F would be equal to the multiplication of 0, 2, 4, 5. Let me see if I did it correct. Yeah. So F would be the multiplication of, or the maximum product of maximum, or we call POS, of 0, 2, 4, 5. Now the conversion between different canonical forms. The complement of a function expressed as the sum of minterms or sum of products equals to the sum of minterms missing from the original function. So for example, if f is equal, f of ABC is equal to the sigma of 1, 4, 5, 6, 7, thus f prime, what is missing in the first one? 0, 2, and 3 are missing. So f prime of ABC is going to be the sigma of 0, 2, 3. By De Morgan's theorem, the same for a max term, f of ABC, if it's the multiplication of 0, 2, and 3, f prime would be the multiplication of, or the product of 1, 4, 5, 6, 7, which is missing in 0, 2, 3. Therefore, m prime of j, lowercase, is going to be mj. So sum of minterms is going to be equal to the product of max terms. So we interchange the symbol sigma and the product symbol and list those numbers missing from the original forms. So sigmas of ones is going to be the product, or the sum of ones is going to be the product of zeros. And I already mentioned it in the table as well. So for example, if f is equal to xy plus x prime z, the f of xyz is equal to the sigma of 1, 3, 6, 7, and the product is going to be the product of 0, 2, 4, 6. So again, the sigma is 1, 3, 6, and 7. 1, 3, 6, and 7. And the ones that are missing, product is of 0. Let me do it with a different color. 0, 2, 4, and 6. Now, standard forms, canonical forms are very seldom the ones with the least number of literals. Standard forms, the terms that form the function may obtain 1, 2, or any number of literals. So for example, the sum of products f1 is y prime plus xy plus x prime y z prime. The product of sum for that would be x, for f2 would be x, and with y prime plus z, and with x prime plus y z prime. And f3 would be a prime b prime c d plus a b c prime d prime. And when we want to implement this, so example for this, we want to implement F1, F2, and F3 using gates. So for example, if I want to implement this one, we have X and Y and together. We have X prime, Y, Z prime. So X prime, Y, Z prime, and together. This is X. This is Y. This is X prime, Y, and Z prime. And we have Y prime as well. So I could connect this to a NOT gate. And all of these are OR together. So big OR at the end. We have Y prime here. This is X, Y. And this is X prime, Y, Z prime. Again, this goes to a Z. And this would expand like this. This is X connected with a NOT to X prime. So we can implement these using logic gates, like the AND, OR, and NOT gates. And this would be equal to F1. And we could do that to the other functions as well. I want you to go ahead and practice it on this one. F2 is equal to X, Y prime plus Z, X prime, Y, X prime plus Y plus Z prime. I want you to implement this using logic gates. Sorry, just give me a second. Yes. Thank you. Great. Yes. Perfect. Yes. Okay. So for the implementations, again, here to make it a little simpler, the inputs are already labeled y prime, but if you want to do it, you can add a y here and connect it with a NOT gate, and here with the x, it's going to be here, and add that with a NOT gate over here. So you can see the two-level implementation of different logic gates in the system. And this is for AB plus C times D plus E, and this is for AB plus CD plus CE. This is enough for today's class. We want to start with the lab. And for the first lab manual, I've already posted the first lab manual. And for the in-class students, it's if you go to your if you go on Canvas and under the 3305-lab, you can see the lab manual. And I want you to go ahead and do parse 1 of the lab manual for today and complete these tables and answer the questions that you have at the end of the lab manual as well, with the ones that are related to the part 1. So for today, we're going to do part 1 of the lab manual number 1. For the online students, please do that at home, and I would put a Dropbox. You have 2 weeks to do part 1 and part 2, and I would put a manual on how to write your report as well. You just have to technically complete the tables and answer the questions. Thank you so much.